Okay, so in this video, we will learn how to calculate the pH of a buffer solution. So in the previous subtopics, such as a weak acid or finding the pH of your salt hydrolysis, we have been using the ice table pretty much, and also eventually using the formulas of the Ka expression. So back in the previous chapters, we have been using we have been assuming your to find eventually find your H3O plus concentration in your solution. So what we've been doing is using A, specific name is A, and while this case we've been for the acid we'll be using 0.01 minus A. So that's was what we have been doing for the previous topics using ice table. However, in this case, this may not be true at the end of the day with respect to the buffer solution. So the reason why is that so is because now your benzoic acid, as discussed in the previous video on why your benzoic acid doesn't undergo much dissociation in this case. So your benzoic acid, okay, so all these are wrong in this case, yeah, because your benzoic acid concentration remains the same as 0.01, and your benzoic also, while being a strong conjugate base, it will also not undergo salt hydrolysis because it was suppressed. Yeah, so do check the previous video if you guys are still confused over this. So actually, yeah, similarly, we're ultimately trying to find the concentration of your H3O plus using your Ka and using the concentration of the progress of the values that you are given. But there is actually a more elegant way of expressing it, or a more elegant way to sort of memorize and apply with, in the case of a buffer solution, which is actually this equation which I want to introduce to you. So actually this equation might look very abstract or look like, whoa, how do you even reach this? Actually, this equation is simply derived from your Ka. So if you guys don't believe or you guys want to see it for yourself, right? So let's try to prove it. So okay, in this case, I'll be using expressing benzoic as your A minus, and your benzoic acid as your Ha. Your Ka will remain as Ka in this case. So yeah, let's say your Ka now it's A minus and H plus. Okay, I won't put H3O plus and Ha. So what are we actually doing here? Ultimately, we're trying to make your H plus the subject of formula. Okay, so it means if H plus wants to be the subject of formula, we will multiply HA concentration on both sides. Because when you multiply on both sides, this will be cancelled out, right? And you divide A minus on both sides. So the equation now will look something like this. Alright. Okay. So pH at the end of the day is negative log H plus, right? So now let's try to just log both sides first for better visualization. So what happens when you log both sides here? So using O level or high school mathematics, when you use logarithm, you can actually get your in my Ingo. Oh no. Oh, okay, it's going haywire. Sorry. So when you log both sides, well, you can get your log. You can express it as log Ka plus log. This case is this first your weak acid over your conjugate base. Now, but we are trying to find pH which is negative log. So if we multiply negative on both sides, so you will get your pH here. In this case, when you negative the whole thing here, when we expand the negative, we will get your pKa, because pKa is just negative log Ka minus log Ha over A minus. And to tidy the equation up, if you want to make this a plus sign at the end of the day, right? If you want to make this a plus sign at the end of the day, we can easily just flip. can just flip. Oh, I'm running out of space. Yeah, but we can flip the fraction here. Oh no. Yeah, you can flip the fraction here. And there you go. That is how actually this equation is derived from your Ka expression. So this would be quite handy to use actually at the end of the day, because ultimately we want to make a H plus your subject of formula. So let's try to solve this question first. Now. So how do you calculate the pH of this solution? So now we can actually put in the skills that we learned from the previous chapter into how to prepare a buffer solution actually. Yeah. So actually knowing how the buffer solution is prepared will give you more clues on what's the right way to go about it. So if we take a look at this question, we are trying to find the pH of a solution when your sodium benzoate, which is your salt here, is added to the same mixture as your weak acid here. So your weak acid is this guy, HA, and your salt here is your NaH. So NaA. So if you look at the previous video of preparing a buffer solution, hopefully this reminds you of the first way, the method 1 of preparing a solution, which is your weak acid together with its conjugate, with its salt that contains its conjugate base. So yeah, when you add both of these into the solution, you literally will get relatively similar concentrations of your HA and your A minus. None of them, your HA will dissociate, while your A minus will not hydrolyze. You check the previous video if you want to know more again, or to refresh. So at the end of the day, what you're trying to do, we use the golden formula again. Our pH equals pKa plus log salt over acid. Okay, this is the formula we will be using. So we're trying to find pH using pKa, and now the unknowns will just be the concentration of A minus and HA. So your pKa, this will be just negative log 6.25 times 10 to the power negative 5. Now how about the concentration of your conjugate base will just be 0.1 mole. Okay, and your HA will just be 0.01. So yeah, you can see the difference. The concentration is around 10. The salt is around 10 times more than your acid here. So it won't be it's not the strongest buffer solution, because ultimately we're trying to achieve a buffer solution where we have equal concentration on each side. But it doesn't matter, it still works as a buffer solution as long as it's within 10 times range. So when you punch all this into your calculator, you will get okay, your pH will be 5.20. Okay, let's hope that I did not make any errors here. Minus log Ka, negative log Ka. Let me just try it again to make sure I'm correct. Log salt. Yeah, 5.20. So that's how you calculate the pH of our solution. Okay, yeah, but this is true. It's good to know that how the buffer solution is prepared. This was method 1 in the previous video. So now let's look at another question here. So now we have a buffer solution that was prepared when you have quite a lot of acid, your weak acid here, that reacted with your strong base. Okay, so I think now for the untrained eye, you guys can't really tell what's going on here, but actually this was a method 2 of solving of preparing a buffer solution, which is partial neutralization. Partial neutralization. So what do I mean by partial neutralization here? So I think since they are all in 1 mole for simplicity simplicity's sake, we know that your weak acid here is in quite a large excess as compared to your NaOH. So if we write the equation out, so let's use a weak acid as Ha again plus NaOH. You get salt and H2O. So your salt, okay. So we can punch down numbers. We actually use a simple mini ice table here to represent what is going on here. So how many moles of Ha do you begin with? We have just 175 over 1000 times 1 mole, which is 0.175, and your NaOH should be 0.075. Okay, initially nothing happened yet, then neutralization occurred. So now since your NaOH is the limiting reagent, all of your NaOH will be reacted away. At the same time, yeah, I shouldn't talk about H2O. We'll just ignore H2O. At the end of the day, we'll get 0.100. Don't have anything for NaOH, and 0.075 for your Na, which is actually your conjugate base. So now that we have, so what's next? Okay, so again, the magic formula pH equals pKa plus log, in this case is your log salt over base. Again, we can punch your numbers in for your pKa. That's negative log, oh, don't even need negative log, it's given already in this case, which is just 4.22 plus, again you have to find the concentration of your your base, I mean your conjugate base, as well as your conjugate your weak acid. Tongue twister here. So how do you calculate your concentration? It's actually just 0.075 mole. This is the amount of moles, right? And what's the new volume here? The new volume here is 250 cm cube. But I won't actually punch these numbers into my calculator yet. I'll just tell you why in a moment. So let's find the concentration of Ha, your weak acid. It will just be your 0.1 divided by 0. The same number here. So if we divide this, if we divide 1 over 2, right, realize that you will cancel out your denominator. So at the end of the day, actually we can use moles to replace your concentration value, just simply because that your volume here are exactly the same, so they will cancel each other out. So to fill up the rest of the blanks here will be just 0.075 divided by 0.100. And what is the answer here? 4.22 plus no. Okay, 4.09 or 4.10 actually. Okay, yeah, and that is how you calculate the pH of a buffer solution.